Yes, so we have started recording. Unfortunately, we did not record the first 5 minutes, but we are trying to show that this S of n comma 3 is lower bounded by omega log n, and we tried to do that by defining treating one element n as special, and then giving a binary encoding to all the other members 1 to n minus 1 based on the permutation family. There was 1 bit per permutation in the family. This was the definition for the binary encoding. The ith bit of a value x is 0 if in the ith permutation x is before n, and 1 if it is the other way around. And then we just argued that B is indeed an injective function from 1 to n minus 1 to the binary strings, because if two points x and y are different elements, the adversary can pick x comma n comma y as the sequence of 3 elements, and there should be at least one permutation in your set sigma I in your family F such that x comes before n, which comes before y, which means the ith bit for x is 0 and ith bit for y is 1, which shows that the encodings are different. So yeah, this is a quick recap of what we did not record. Okay. Now, from this, can you see that m has to be at least log 2 to the base n minus 1? This last step is something which is, not even clever. Okay, this is something which we should always see, because we are saying from this 1 to n minus 1, we are having a binary, we are having an injective function f to this f2 to the power n. Okay, what is f2 to the power n? F2 is just, now you don't even have to think about the algebra. It just contains 2 elements, 0 and 1. And to the power m is to indicate that it's a Cartesian product of m such things. So these are m length binary strings. Now, if this function is injective, then that means this cardinality is lower bound for the codomain's cardinality, right? So this means n minus 1 is less than 2 to the power m, or n minus 1 log 2 is less than or equal to n. So since it's m is an integer, we can also, without any free of cost, we can add a ceiling. Okay, so this is a standard thing, right? Whenever we try to do a binary thing, this is the starting of what is known as an entropy method, but this is, too simple to use such a fancy term. Okay, so this completes the proof that S of n3 is greater than omega log n, because log n and log n minus 1 are almost the same. Any is it clear to everyone?
Yes, sir.
Okay. So we have now 2 different lower bounds, right? We have now 2 different lower bounds. By the way, do you all agree that S of nk, so if k is larger than or equal to 3, S of nk is greater than S of n3? Because this k scrambling becomes only harder with larger number of elements, right? So if you have a 4 scrambling family, it is automatically a 3 scrambling family, right? Like you may be interested in scrambling some sequence a comma b comma c. What you do is you arbitrarily pick a 4th guy and call it d, and then the 4 scrambling family will give you something like some sigma where a less than d, then this will satisfy your requirement. Okay, so any k scrambling is also k minus 1 scrambling. It is also k minus 2 scrambling, and so on. Okay, so we have now 2 different bounds. So this will give you this log 2 to the base n minus 1. And when we started this, we also said we have a lower bound of k factorial. Okay. Now, both bounds are interesting, but both bounds seem to be partial. Okay. In the sense that in the first bound, you don't have a dependence on k. And in the second bound, you don't have a dependence on n. Okay. So I think now that Abraham reminded me, maybe I would have written the lower bound somewhere in the slide here, right? So can we kind of have both of it? Okay, dependence on k. So now our attempt is to show that S and k is lower bounded by both a function which depends on both k and n. Okay. So here there is a this again sophisticated. I mean, in the sense of a clever trick. But, what is when do I use the word clever? I use the word clever when for things which are difficult to find out, but not so difficult to understand. When it is explained. When I call sophisticated, it would mean both. Okay, it is difficult to find out as well as difficult to explain. Okay, but here also the first idea is the kind of magic idea. Okay, so yeah, so we now think about k to be a large number. Okay, at least think about something like 4 or 5. Okay, to have a Mendel picture, it has to be larger than 3. Even 4 is fine. Okay, so think about k equal to 4 or 5. And what are we looking for? We are looking for a bound that is better than this log n minus 1 that we proved earlier. Okay, so here the idea is in the other proof, we first took this universe, which was 1, 2, up to n, and then took n as a special guide. Okay, now what we will do, like let us say we are now focusing on k equal to 4, or maybe 4, maybe you may not get the picture. So let's focus on k is equal to 5. What we will do is we will treat these 3 guys as special. Okay, the last 3 guys we will treat as special, and this lower bound argument of log 2 n minus 1 essentially was by putting these guys inside and having your x on one side and y on the other side, right? Like we had this. This is the thing that I want you to recall. Okay, but now we are going to ask something like, for any x and y, we will have n minus 1. Sorry, n minus 2, n minus 1, n less than y. But I can also demand another permutation of these 3 guys, right? And I have 6 options, 3 factorial options in general. Okay, so this is the idea that we are going to say. I want you to, I mean, I haven't explained it clearly, I know, but this is the idea that we are going to implement to analyze this lower bound. Also noting that first demand and second demand cannot be served by the same permutation. Okay, because the relative ordering among our special guys are different, so they cannot be the same permutation. So what we start off with is we again have this permutation sigma 1 to sigma m, which is 5 scrambling. Okay, for n. What we first do is we split this into 6 groups. Okay, and these are going to be disjoint groups. There's going to be a partition of f into f1, f2, all the way up to f6. Now, what are the permutations which go into f1? Those are the permutations in which this n minus 2 comes before n minus 1 comes before n. Okay. What is this? This is where, let us say, n minus 1 comes before n minus 2 comes before n. Okay. So now you see, depending on the 6 possible permutations of these 3 special guys, you have 6 groups, right? So you have 1 group for 1 permutation of these special guys. Is this split up clear?
Yes, sir.
And is it also, more importantly, is it clear that this is a partition in the sense that for if you take a if you take one permutation, it is unambiguous as to which set it will go to. You ignore all the other numbers, only retain these last three guys, the special guys, and then check what is their relative order. Okay, that will decide in which bucket you will put in. Okay, so you have taken your whole set of permutations and split it into 6 buckets. Okay, anybody wants to guess the next step?
Same as the previous case, the binary encoding.
Yeah, but I'm looking for one more phrase.
Whether no.
Yeah. So what I'm trying to, what we will do next is each of the buckets size we can lower bound like the previous argument. Right? So for example, I can easily see that F1 is lower bounded by log of n minus 3 in this case. We don't have n minus 1 because 3 guys were special, so they move off, but this F1 we can lower bound by log 2 of n minus 3. How do we say? We again, for this alone, we give a binary encoding b from this n minus 3 to f2 power m, where bi of x is defined to be 0.
Whether it comes before this.
0 if x is before this order, right? N minus 2, n minus 1, n. Okay, we define it this way. I mean, this is unnecessary. I could have just said x is less than n minus 2. The other two are corollaries because in F1 everything is in this order, but I'm writing this for a reason which will be clear now. And 1 if n minus 2 is in this. Okay, these ordering are sigma i's. Okay. Sigma I n minus 1 sigma I n less than x. Okay, so this will just prove that F1 is less than x. Okay, I'm kind of writing it this way because I want to ensure that when I'm trying to when I'm trying to argue for a lower bound for F1, I need to make sure that the permutation where this happens is inside F1. That is why I wrote this whole range here. Okay, that's the only reason why I wrote this whole range here. So this ensures that this permutation is present in F1. Okay, and remember this surely, whichever the adversary has picked. Okay, now when you go to this lower bounding argument, you will say that if for any x not equal to y, okay, I will have this order x n minus 2. The adversary will pick things in this order. Why? I am sure that because of this relative order, this permutation is from F1. So within F1, you have a permutation like this, which may be for some sigma I element of F1, which means sigma I bi of x is equal to 0 and bi of y is equal to 1. This proves that b is injective inside of this. B is injective, and hence the rest of the argument is. And now, since all the partitions were disjoint, the size of f, the same argument applies for f2, f3, etc. So you can have 6 times f1 as a lower bound. Okay, so this proves that s of n comma 5 is less than or equal to 6 times log n minus 3. Okay, so now I want you to guess, if I do this trick for a general k, what would be the expression which will come?
N minus 2 factorial.
Not n minus 2 factorial.
K minus 2 factorial.
K minus 2 factorial.
Correct. So this 6 is nothing but the special guys factorial. The number of special guys is going to be k minus 2. K minus 2 factorial. And what would be inside of the log? N minus number of special guys, right? So number of special guys is n minus k minus 2. Okay. But this you can ignore for large n compared to k. This is almost like log n, but you have got a k minus 2 factorial, and we succeeded in our attempt to find this kind of a function, and we in fact found out a very good function, some k minus 2 factorial to log 2. Okay. Now there is further scope to improve it. For example, we did not consider permutations in which these guys go inside and so on. So the best known bound is, I think, k minus 1 factorial rather than k minus 2 factorial with an added constant like e or something. Okay, but we won't discuss that. But a search will give you that result. Okay. Yeah. So this is, I mean, I was in two minds whether to discuss these lower bounds in full detail or not, because these are not probabilistic arguments. But I still thought I'll do it because anyway the ideas are good. Plus, it kind of tells you that the probabilistic argument is not far from being tight. Okay, there is still some gap. Like here, there is an order of k cube gap between the lower and the upper bound, but it is still between the lower and upper bounds we proved. Between the best lower and best upper bounds, there is only a k squared gap. So yeah, that's also one reason I wanted to convey. I mean, at least give examples where this is tight. Similarly, for that hashing also, you have a similar, this logarithmic bound. I will urge you to first try proving this ln bound separately, right? And then trying to combine it like this. Okay, this binary encoding and then using that to give a lower bound argument is very common. If you have any comments, please. Otherwise, we will move to the tutorial. Where is the tutorial sheet? Okay, so we have only 20 minutes or so. So we won't work out the details of the tutorial. I'll just ask, we'll maybe start each question, how to do it, and then leave it as exercise. So any attempts for, please read the question and tell me if you are thinking of any attempt to solve. Okay, firstly, read the problem. What is a 1,1 separating family of functions?
Perfect hashing family.
It's simple. It is, you are correct, but it is simpler than that. It's a perfect hashing family for pairs. Okay. So any other answer? Does anybody else want to give it's actually a very simple problem. If instead of this 2,2 separating, I had asked for 1,1 separate. Then what is this family of functions? So let me read out. Okay, a family f of functions from n to f2, 0, 1 is called 1,1 separating for n if for every two different elements little a and little b. Okay, I'm kind of not reading two sets A and B. I have to read one sets A and B, but then one sets instead of, it's a heavy term, right? Instead of saying one sets, disjoin one sets A and B, I'm just saying two distinct elements, little a and little b. Okay, there is a function f in this family which maps little a to 0 and little b to 1, or vice versa, little a to 1 and little b to 0, which is essentially saying a function f which maps little a and little b to different values. Show that there exists a separating family of size order log n. What would be your separating family? No idea? Rajesh, what do you think?
So just I understand the problem, but
Yeah, so that is also one issue with many of these questions. The way it is written is with an eye to generalize. Okay. Yeah. So here, at least when we say a 1-1, when you say a 1-1 separating family, it is very easy to identify one. You take the binary encoding of a number. Okay. So if, and here I mean just a direct binary encoding, not a complicated binary encoding like we did for the lower bound proof that we just saw. It is like, 1 is mapped to 0, 0, 0, 1, 2 is mapped to 0, 0, 1, 0, 3 is mapped to 0, 0, 1, 1, and similarly n is mapped to this. Okay, you can even do a 1 minus binary encoding of x minus 1, then it would be slightly better, but let's not do such simple optimizations, right? Now, my functions are the following. Okay, this is my function f1, the first bit position. This is my second function f2, right? So what is fi of x? Fi of x is equal to the ith bit of x represented in binary. Okay. So fi of x is nothing but you just express this number x in binary and take the ith bit. I claim that this is a 1-1 separating family, right? Because if you take any two distinct elements, little a and little b, right? If you take any two distinct elements, little a and little b, then the binary encoding of one will be different from the binary encoding of the other. What does binary encodings differ mean? That means they differ in at least there exists a bit position I such that the ith bit of A2 and B2 are different, right? Which means fi of A is not equal to fi of B. So this fi is the function in the family which will separate A and B. Is it clear?
Yes, sir.
Okay. So this doesn't need any probabilistic method. You do a direct encoding, you can do this, right? But you can do the same thing using a probabilistic method also, and doing it that way is going to give a slightly weaker bound, but then you can easily generalize to 2-2 separating or even KK separating kind of a scenario. So what would be a random way of assigning these functions f1 to fm? Let's stick to 1-1 separating to keep it simple. Right? What would be a random way of generating this family of functions f1 to fm?
Assigning 0 and randomly.
Correct. So now let us say you create f1 by going through each point in 1 to n, toss a uniform coin. If it lands heads, give it 0. If it is tails, give it 1. And this you have to do independently for the n points. This gives you f1. Repeat the same process independently to get f2. Repeat the same process again independently to get f3 and so on. Now this is the most random thing that you can do. It's also the simplest and it is the most random thing you can do, right? So pick this f1 to fm independently and uniformly at random. That's your first step. Okay. Now analyze, calculate the probability that this family f is equal to f1 to fm is 1-1 separating. Okay, either we calculate this probability or its complement probability, right? And you will see that this with some like if you put some constant times log n, you can make the good probability greater than 0 or the bad probability less than 1. Okay, so I leave this details to you. That is how a probabilistic method will work. Now the same technique you apply and just replace this 1-1 separating with 2-2 separating. But here when you analyze the probability, it is slightly going to be different. So if you take some set A is equal to A1, A2 and a disjoint set B is equal to B1, B2, the probability that these are separated in some function fi would be, there are two ways in which this can be separated. These two can be assigned 0 and these two can be assigned 1 or entirely different. Okay, so this happens with probability 1/2 to the power 4, because A1 has to be 0, which is with probability half. A2 has to be 0, again probability half. B1 is 1, probability half. B2 is 1, probability half. All of them are independent. Okay, this is like the coin toss. If you are going in the order A1, A2, B2, B1, B2, you should get tail, head, something like that. But one more option is valid, which is where you get 1, 1, 0, 0. So this is the good probability that you have for one function to satisfy a given set. So the bad probability of this is equal to 1/8. Okay, so the bad probability is 1 minus 1/8. This is the probability that fi does not separate A and B. Now, since you have m fi's, the probability that none of them separates is this much. And now the last step would be the union bound, because if at least there is one pair of sets which is not separated, your family is not separating. So this union bound will have something like these many terms. N choose 2 choices for A and n minus 2 choose 2 choices for 2. And this is what you want to show to be less than 1. So if you, ignore all this is approximately enough to show that 7/8. Now you take a log, you will see that m has to be only of the order of log n. There will be a constant. I do not know what would be the constant. The constant will surely involve 4 as well as the reciprocal of log of 7/8 and so. But that is okay. So this is the idea. I want you to work this out further. The next question is also very similar to the scrambling we have done. In fact, this is easier than the scrambling. So the upper bound would be same. but here also I want you to think of a lower bound also. Okay, at least for 3 mixing, think of a lower bound. Yeah. Question 3. Okay, question 3 is again, no, I don't think we have, yeah, this I will leave you to think. Maybe next week we can continue discussion. Okay, this question is there. This is directly a worked out example in the textbook. This is, yeah, Allard and Spencer theorem 1.33. But before looking in the textbook, I want you to go back and look at that Sperner's lemma, where we showed that the maximum size of an anti-chain is and choose n by 2 and see if the same idea can be extended to show this. Okay. Yeah, so this is about the